Hello, everyone. My name is Rafael Morales, and for my third project, I work on repeated second price auction with bandit feedback. I chose this topic because it is very similar to how real digital advertising market work today. In real auctions, you always never have full information. You don't know their bidder's value or their strategy. I wanted to explore whether an agent could learn to bid well in this kind of environment where the only feedback it gets is whether it won the auction or what price it paid. A second price auction is a game where all bidders submit sealed bids. The bidder with the highest bid wins, but they pay the second highest price. Now let me explain the model I built. I simulated a game with three bidders. In every round, each bidder receives a private value between 0 and 1. Their goal is to choose a shading factor S. This value determines their bid. For example, if S is equal to 1, they bid truthfully. And in this type of action, bidding truthfully is actually the clear strategy. If I allow the agents to see everyone's bid, this project will be trivial and they will simply calculate the optimal bid and wins immediately. That's why I use bandit feedback to hide that information and force them to learn. To formulate this as a multi-arm bandit, I define the shading factor of discrete step of zero point 0.1 from 0 to 1.5. This creates 16 distinct choices that the algorithm can pull in each round to test which one works best. The key challenge in this setup is the feedback. After placing a bid, they only see two things. Did I win? If I won, what's the price? This makes learning difficult because the agent must estimate counterfactuals. What would happen if I had picked the other 115 choices without seeing the actual bids of the other players? To solve this problem, I implemented and compared two different algorithms. On the left, we have EXP3, a modified version of a multiplicative weight update algorithm. It is a standard method for adversarial bandits problem. EXP3 keeps the probability distribution over all shading factor and updates every round. It is designed to be smooth. It always explores a little by using a parameter called gamma. This prevents the agent from becoming overconfident and helps to keep learning. On the right, we have FTPL, follow the perturb leader. This method works very differently. It keeps running a scoreboard of rewards and adds random noise before choosing the best strategy. Because of this, FTPL is sticky. It often commits to one shading factor for a long time. Since this is a bandit setting, I had to modify FTPL by using a Monte Carlo simulation to estimate missing probabilities and then apply inverse propensity scoring to update the agent. I also added a safety valve. If FTPL stays stuck on the same action for too long, it forces a exploration step. This prevents the algorithm from staying locked in a bad strategy forever. Now let's look at the results of the simulation over 50,000 rounds. On the left side, we have the chart using EXP3, and on the right, we have the results of FTPL. The top plot for each algorithm shows the accumulated regret versus number of rounds. With EXP3, all bidders behave very similarly. You can see a change in the slope around round 10,000, which shows the algorithm is definitely learning. Below the regret chart, you can see the heat map chart that shows how the probability distribution changes over time. And the bottom plot shows the final distribution for each bidder. Most of the probability mass ends up on 1, that is truthful bidding value, which confirms that the algorithm learned the optimal strategy. The probability for the other shading factor are not zero because XP3 always explores a little, controlled by the gamma parameter. In contrast, FTPL on the right is much more volatile. The accumulated regret graph shows a positive trend, meaning the agents are still learning, similar to XP3. However, FTPL does not keep a smooth probability distribution. Instead, it uses cumulative score to decide the leader. When the bidder gets stuck on a bad strategy, not close to say the factor of 1, the regret increases quickly. You can see this as a vertical jumps in the cumulative regret plot. Thanks to the safety valve and the Monte Carlo probability estimates, a single lucky win can cause a big score update. When that happens, the agent suddenly discovers the better strategy and switches, which flattens the regret curve again. In this final chart, I compare an optimized EXP3 agent against the FTPL over 50,000 rounds. I ran the simulation 5 times using different random seeds and averaged the results. The blue line, EXP3, stayed below the red line, FTPL, meaning EXP3 learned the optimal strategy faster and it took fewer losses over time. The shaded regions show the variance across the 5 runs. EXP3 remains stable no matter the seed, while FTPL shows a very wide spread. This tells us FTPL is much more sensitive to initial conditions. In conclusion, the performance difference comes from how each algorithm behaves. EXP3 keeps a smooth probability distribution over all the actions and always explore a little, controlled by gamma, which helps us adjust quickly when things change. FTPL, however, is much more sticky. When it chooses a strategy, it often stays with it for a long time because of how the follow the leader idea works. With the modification I implemented on FTPL, such as adding noise, using Monte Carlo for bandit feedback, and including a safety valve to break up bad actions, FTPL can eventually find the correct strategy, but it wastes many rounds stuck on poor bits before switching. Thank you for your attention. With this, I finish the presentation.